Hello everybody, we will continue our lectures on kernel filter, and logically we have derived in the linear domain first, followed with discrete time as well, and logically we will extend this to something called extended kernel filter, and then followed with a little bit concept on uncentered kernel filter, which are typically used these days in practical applications. So, the problem is something like this. First is continuous, okay, before that a little bit recapitulation of what we call as continuous discrete kernel filter is still in the linear domain, but system dynamics can be continuous, whereas the measurement is discrete, and that is the one which will actually, this platform is the one which will help us for external kernel filter and all that. So, the problem is like this now, there is a continuous time linear system, time varying of course, whereas I mean system dynamics is continuous time, whereas the measurement equation is discrete time. Okay. Now, here is a kind of a mixed situation, but that is typically real life. In real life we have system dynamics represented by differential equations naturally, whereas measurement equations are typically discrete equation, where it comes at what each sample of measurement sort of thing. Okay. So, then here is a W which is actually continuous time. So, it is represented as this expression, it is Q T minus tau, okay, and whereas this okay, essentially, well, we can think of this as something, well, anyway, this will not bother about that. In other words, Q k is when t is t k, otherwise q k has no meaning actually. But having said that, if t is equal to tau, then only it is 1, otherwise it is 0 basically. Okay. Remember that. Then expected value of this quantity V k times V j transpose is R k, Kronecker delta now. So, unless this k is equal to j, everywhere else, I mean unless k is equal to j, it is 0, if k is equal to j, it is 1 actually. So, using this kind of notation, again we will go to the mechanism. The idea is again this prediction correction like that actually. So, start with some value at t naught minus value, which will also assume that is the corrected value, okay. That is initial guess sort of thing. Then we propagate it and get a measurement here. So, update it, and by the way, if you get a measurement at t naught itself, then you can update it also here itself and then proceed. So, again so coming back, this is the propagation, okay. Then in prediction we predicted, but based on the measurement this correction happens here, then again we predict, and then based on measurement we have update here and things like that actually. Okay. So, principle is like this, propagate the state estimate model forward from t k to t k plus 1 using the initial condition x k hat plus, okay, and then correct the value from minus to plus, okay, at k plus 1 using the measurement vector y k plus 1. Now, the measurement is available at discrete time steps only, okay, and hence the continuous time propagation does not involve any measurement information actually. That is, you can derive it also, and it turns out that earlier there was some I mean it had some measurement information as well actually, if you remember the previous lectures and all that, but now it does not actually. So, P dot takes a rather relatively simpler expression like this, right, in this form actually. So, we have this now the expression for P dot is something what we need to derive, and let us say we have this x dot is something like this, and the x hat dot is this form, because noise cannot be taken into propagation equation. So, we drop the noise term while operating on the prediction mode. So, obviously, the error between that is nothing but this x dot minus x hat dot, which turns out if you take the difference between that, b will go. The rest of the terms will become something like a times x minus x hat, which is a times x tilde plus g times w, something like this. So, again this is a time varying input. So, time varying input we can solve this x hat of t, okay, using this, but remember these are all time varying systems. So, can't use exponential term, but we can always use state transition matrix. So, state transition matrix phi t t naught, you put it back here and then get a solution for that. then R W X tilde turns out to be expected value of this expression, and right, it is W times X tilde is like this. So put it there, but again because of orthogonality this expression this term does not matter, only this term will matter, and then it will excite this again delta function and things like that, and ultimately it will turn out to be something like this only. Here is the delta function which will come into place when expected operator it goes inside the integral. So this is nothing but by definition Q, so it turns out to be QZ transpose sort of thing actually. Now going back to this actually, strictly speaking this there is so there is no Q there, I mean QK does not make too much sense because it is a continuous time. It is evaluated at time Tk, then it is Qk. Alright, so this is what it is actually. So alright, now expression for P dot is like this by definition. So again you separate it out these two terms, and this term plus the same term transpose again. So this term happens to be something like this. So expected value of all that, and then expected value X tilde transpose is something like this, plus GE W times this actually. The expected value will come all the way and sit here actually. The W is a random variable that, so it will get coupled with that. But I mean this quantity is nothing but P by definition. So A times P plus this quantity is nothing but, we just derived it as half of QZ transpose. So we put that there and it will end up with this. So P dot happens to be this term plus the same term transpose. So that is why you get AP plus P is a symmetric matrix. So P transpose A transpose means P times A transpose here. And once you expand this transpose, it will become P transpose A transpose, but P transpose is same as P. So that is P and A transpose is here. So AP plus PA transpose plus this quantity will remain exactly same, but half will go now. So it will have something like this. That is what we told. I mean this P dot takes the expression of like this actually. Alright, so we got an expression for P dot now basically. So that is all we probably needed. So to implement that actually. So how do we implement really? We have this system dynamics here, and we have this measurement equation in discrete time. We initialize it again, and P naught minus also needs to be initialized. So gain computation can happen this way, same thing as before. Alright, so this update can also happen as same thing as before. We do not have to derive again, rederive everything, because these are very similar to what we have done in discrete time system, I mean discrete time platform. Only thing is the update equation, the prediction equation, the propagation equation sort of thing can happen now using some sort of higher accuracy numerical integration, high accuracy basically. In other words, this can be retained as something like continuous time expression, and then using this higher order numerical integration schemes, you can actually propagate it with much lesser error actually. That is the only difference. But when you do this, this P dot expression, be careful, P dot expression like LTI system do not, I mean like continuous time system do not use it. This additional term is not there, it stops here actually. P dot is PA plus, AP plus PA transpose plus EQZ transpose. That one more additional term what we had in pure continuous time derivation process, where measurement was also assumed to be like a purely continuous variable, is not there basically. So just be aware of that. So otherwise the implementation is fairly similar to what we do, very similar to what we do in discrete time domain. The only difference is probably in the propagation stage you use continuous time expression and then excite some sort of a higher order numerical integration theme to propagate it in a much better sense basically. So that is how this platform. Now going back to this idea of this prediction correction things like that, we can now graduate ourselves and tell, okay, well, we know something so that we can actually think about handling nonlinear systems as well basically. Let us see in a short while now. So couple of comments here. First of all, this P dot expression is something is a continuous time Lyapunov equation, now, because this nonlinear term is no more there in terms of P basically. Okay. So, it this P dot expression had a P transpose and things like that, that term is no more there. So, it boils down to be something like a linear differential equation in the form of P, and it takes somewhat close to this expression of what is called as Lyapunov equation. Okay. That is just an observation actually. Okay. And then this continuous discrete common filter facilitates the uses of non-uniform delta t also. Okay, that is another important point. We really do not have to have that this intervals T0 to T1, T1 to T2 and all, the intervals need not be same basically. So, prediction can go on as long as there is no measurement information, and as soon as there is a measurement information, it is a valid information by the way. We will talk about that, what is called as outlier and all that is not there. So, if you consider that as a valid information, then as long as it does not come, we can continue to operate on prediction mode. As long as there is a valid information comes to the sensor, we can update it actually. So, this does not tell that okay, there has to be a uniform delta t, there is no reason for doing that actually. Okay. So, that is another advantage. Okay. Alright. So, you use this continuous time expressions to propagate this way. So, do not get confused that these expressions are not there, they are still there embedded into this actually, okay, this equation basically. Start with some initial condition, propagate to the next time step actually. So, when you propagate essentially you start with some condition at k and you propagate to k plus 1 minus, okay. Implicitly it happens actually. Alright. So, finally, after all this we are at a stage where we can actually talk about EKF. And if you remember this my very first comment about Kalman filter, the Kalman filter has become quite popular and quite vast applications and things like that, because of this platform, this external Kalman filter, and fortunately it works for a variety of problems actually. Okay, even though it is a concept and it is there is no rigorous proof and things like that, but still it operates I mean it works successfully for many cases actually. So, that is why it is quite popular. So, let us see that. Before we derive or outline the concept, some facts to remember. First thing is nonlinear estimation problems are considerably much more difficult than the linear problems in general. Okay. And EKF is just an idea and it is really not a cure for everything. In other words, if you have a typical peculiar problem with high nonlinearity or maybe kind of non-Gaussian noise or color noise, things like that, then EKF may fail also. So, just be aware of that. Okay. The problem with nonlinear system is that the Gaussian input does not necessarily produce a Gaussian output. Okay. So, that is the one of the major difficulties of this nonlinear systems in general actually. Okay. So, but however, the nice thing is the EKF is, even though it is not really optimum, that it has been successfully applied in many nonlinear systems over the decades. So, in a variety of applications, and that is what I have been insisting on actually. Okay, what is the fundamental assumption? There is a nice idea here. It tells you that the fundamental assumption in EKF design is that the true state x t is sufficiently close to the estimated state x hat of t at all time. Okay. So, our estimate is not really bad at any time, including initial guess by the way. Okay. That is the fundamental assumption, and hence it requires that we really have a rather reasonably good initial guess for x hat of t as well actually. And all the time it will assume that okay, my true state is close to the estimated state, and hence I can actually represent the system dynamics as some sort of a linearized system dynamics around this estimated value, because the error between estimated and true is not high. That is the assumption actually. Okay. Alright. So, with all that fact in mind, let us go to the EKF domain. And first we will see this continuous EKF, that means everything happens in continuous domain sort of thing. But ultimately we will end up with continuous discrete form also basically. Alright. So, when we talk about continuous formulation, we have this problem x dot is f of x u t plus g t w t, and y is nothing but h of x t plus v t. Everything is continuous, even measurement is assumed to be a kind of a continuous variable with a very high sampling rate and all that actually. The other assumption is f and h are also continuously differentiable functions, okay, and as usual w and v are assumed to be uncorrelated zero mean Gaussian white noise actually. So, those standard assumptions are there with us. Now, this is the concept that facilitates EKF. What we are telling is the true state is can be represented as something like this. Obviously, it can be represented always like this, something like true state is estimated state plus error in estimation, that is by definition. But what you are assuming is that x tilde is small, and that is where you can bring in this linearized concepts and all that actually. So, when you write something like this expression what you had in system dynamics now can be written something like this using Taylor series. Okay. So, using Taylor series and neglecting higher order terms, okay, we can go back and tell, okay, this expression I want to expand in terms of Taylor series around x hat of t. Okay. So, the very first term will take x hat, the second term will be del f by del x evaluated at x equal to x hat, okay, times x minus x hat, and x minus x hat is x tilde basically. Okay. So, right. So, this is what it is, the first term, and then this term Jacobian matrix sort of thing into x minus x hat. Okay. And similarly, you can write this nonlinear function also. If we expand using Taylor series, we can write it something like this actually. Now, what we evaluate the expected value of this function, what we have derived here. If we take expected value both sides, and it turns out to be expected value of first term plus this is a constant, this kind of a known numbers basically, there is no random variable here. So, this can be I mean the expected operator can be pushed inside here, this is a deterministic quantity sort of thing. Okay. Now, expected value of x is by definition it is x hat. Okay. So, this is the nice observation actually, by definition it is nothing but x hat. So, it all turns out that x hat minus x hat. So, it gets cancelled out altogether basically. So, essentially what it tells you that expected value of this quantity which contains some sort of random quantities and all is nothing but that quantity only, as long as this linear expression remains valid, I mean linearized expression remains valid up to first order term basically. Okay. And that is the beauty. Okay. So, we take expected value of this is nothing but the first term plus this term into 0 basically. I mean that is the whole beautiful observation there. So, this gives us a lot of simplicity basically. So, expected value of this is nothing but that. Similarly, the expected value of h is nothing but this. Okay, exactly same thing is that, again expected value of x will come here and x hat minus x hat will become 0 basically. Okay, so, turns out to be like this. So, what you can represent is if you go back to our observer dynamics sort of thing, we get motivated by these observations and tell, okay, because expected value sense this does not play a role and it only has that part of it. So, how about proposing an estimator dynamics or observer dynamics to be something like this. The first term is kept as it is plus Kalman gain times innovation. Innovation is true observation, I mean true output minus the expected output or predicted output basically. Okay. And predicted output which is expected value of this is nothing but that. I mean that observation again helps us actually putting it there. Okay. So, we have this x hat dot is nothing but f of this plus Kalman gain times innovation which is y minus h of this. Okay. Where y hat is nothing but that. Okay. This is predicted output sort of thing. So, this is your observer dynamics. Now, what is error dynamics now? Error is defined as x minus x hat. So, x tilde dot is x dot minus x hat dot and x dot is this quantity minus x hat dot is nothing but that quantity now. Okay, this is our observer dynamics. So, put it back here whatever we know here and then first term and first term can be put it this way and rest of the term can be kept out actually. So, this first term and first term we combine here and then Kalman gain terms which is one coming from here and one coming from here, we put them together plus GW minus KEV, GW coming from here and KE times V comes from here with a positive sign here, but ultimately there is a negative sign. So, this is what it is. Now, if you see these quantities, okay, you go back to this minus, I mean this quantity, okay, this minus that now. So, this minus that is nothing but this quantity basically. So, we put it back there, that quantity. And similarly, if we talk about these two quantities, is nothing but this quantity now. Okay. So, we put it back, okay. The total quantity, what I mean, okay. This quantity the full and this quantity the full. Okay. So, put it back plus GW minus KEV. Now, by definition, we define this is del f by del x evaluated at x hat is nothing but A of t. It keeps on changing because x hat keeps on changing. So, it is not a constant matrix, but it is time varying A of t sort of thing. Similarly, this is nothing but C of t. Okay. So, ultimately what we will end up with is x hat x tilde dot error dynamics is A minus KEC, okay, times x tilde plus GW minus KEV, where this is all time varying and this can be defined as something like A naught. So, the beautiful observation is the aerodynamics is exactly same as the aerodynamics derived for time varying linear system case, and hence everything else remains same. We do not have to derive it again, we just simply can write it actually. Okay. So, hence the dynamics of the covariance matrix we can straight away write it using this linear time this time varying linear system case. We just go there, see that and write it exactly same, because the aerodynamics is exactly same. So, everything the error covariance matrix dynamics will also remain exactly same. The idea there. The only thing is, remember, A of t and C of t are not really given to us, but they have to be evaluated every time at the most updated value of this x hat actually, and that is the only difference. So, what is the summary of continuous time EKF? We have the system dynamics and our initialization has to happen first, then we compute the gain that way and then we propagate it that way. We have this filter dynamics or propagation dynamics, we can use it to propagate x hat of t, and we have this covariance matrix dynamics which you can use to propagate P of t actually. Okay. The only difference is A and C has to be evaluated every time around this x hat basically. So, that is the summary of continuous time EKF. Now, how about continuous discrete EKF where we can merge these concepts again, and here the question is you have the system dynamics as in continuous time, whereas the measurements are available only at discrete interval of time. Okay. So, what is the idea here? When there is no measurement, that means without the availability of measurement, we can propagate the state and covariance dynamics from xk plus to xk plus 1 minus, and similarly pk plus to pk plus 1 minus actually. Okay. But we can propagate now using the non-linear system dynamics. Okay. We really do not have to use a truncated linear dynamics and all that actually. We can go back to that and tell okay, this is anyway a propagation. So, we can use the real non-linear system dynamics to propagate. Okay, but the covariance dynamics we can't derive it that way because that is difficult. So, we can still use the linear covariance dynamics actually. But remember, it is actually, it turns out because there is no measurement in between actually, because this covariance dynamics had this term which made it nonlinear. It happens primarily because we have this continuous time measurement is there everywhere actually. Okay. But if it is not there, this term is not there. Okay. So, we will end up with this P dot is some sort of a linear differential equation, this one plus the last term actually. So, that is what you will use. So, we propagate this P dot using this linear covariance dynamics sort of thing. Okay. But as soon as the measurements is available, you update it and we update from minus to plus value here for the state and minus to plus value for the covariance matrix also. So, what is the summary again? In discrete time continuous discrete EKF, we have this form, okay, which is x dot is something like f of x u t plus g t w t, y is like this is continuous time, but this is discrete time. So, we initialize both the state and covariance matrix, okay. Then we compute the gain, okay. Wherever there is a measurement coming, that point of time it will operate. We quickly compute the gain, use it for update and update covariance matrix also, and then go back to this dynamics in continuous time that we know and propagate it actually. So, using the nonlinear dynamics, we propagate from xk hat plus to xk plus 1 hat minus, and using this linear error covariance matrix equation, Okay, we propagate from pk plus pk hat plus to pk plus 1 hat minus actually. The thing is we have to evaluate this matrix here, okay, and this has to be evaluated all the time actually, okay, using this x hat of t. Okay, so this quantity, this ck minus has to be evaluated and at has to be evaluated while propagating this actually. This is the only difference, otherwise we are pretty clear how to operate EKF now actually. So, the equations are not difficult or it is not difficult to understand really, but there are many issues there which makes the implementation of EKF a little bit tricky issue. So, in some sense there is a little bit of art involved and experience comes very handy actually here. But there are several other ideas around EKF. The first thing that comes to mind is something called iterated EKF. Okay. So, this idea is like that. One way of improving the performance of EKF is to apply the local iterations to repeatedly calculate these guys, okay, and each time by linearizing about the most recent update. Now, what is the whole idea there? Wherever there is a measurement, we quickly compute the gain, okay, we quickly compute ck minus 1, ck minus plus, ck minus first, and then quickly compute Kalman gain using this ck minus, and then we compute this. Now, the moment we update this equation xk plus x hat k plus, we have updated this value to this value. Now, the moment we update this, okay, this value, then again we can evaluate it about that value. Why operating it based on a previously predicted value? We do not have to do that. We have updated value. So, we take that and put this updated value here. So, we get a new C. Using the new C, we can compute a new gain and then again come back and update, and this cycle can continue basically. So, that is called iterated EKF. We can keep on doing that, okay, and that is called iterated EKF. And you can actually fix a number of iterations, there is no point in waiting until stability and things like that, and then proceed further. So, like some people can have 2, 5, 10, I mean you can fix it based on your computational platform and computational capability, things like that, and then operate it based on that. It is still based on EKF, external Kalman filter, but it is now doing several iterations based on the same measurement actually, just because your C matrix is changing basically, because the moment you update it, there is a different value of x, and hence your C matrix changes, and again you keep on iterating on that basically. So, that is the first idea, iterated EKF. And there is a parallel development which is also called linearized Kalman filter. Well, it is actually people thought about it initially, it is a kind of a competitor for EKF and all that actually. Well, let us see what is the idea there. Okay. So, idea here is something like this. This approach involves linearization about a nominal state trajectory which is selected a priori instead of the current estimate. So, what happens in estimating about current estimate is the transients become quite bad. Initially, you do not have any idea about what you are doing, or the error value can be very high. So, the very fundamental assumption that your true state is close to the estimated state or best available information is not there. So, that is the fundamental difficulty of EKF. So, people thought, well, that is the case, why do I bother about that? I really do not have to do that. But all that I need to know is some sort of a linearized approximation of the nonlinear system dynamics. So, in that sense they told, okay, I can assume something like a x bar of t which is selected a priori, and I will linearize it about it actually. Okay, what the meaning of x bar of t? Let us say a satellite orbits and things like that. So, you talk about orbital corrections and all that actually, suppose you want to do that. So, if the satellite has a kind of a known orbit, the known orbit information is already available basically. So, using that information we can think of operating based on, I mean you can think of having a Kalman filter implementation based on that assumption really. Okay. So, then what you tell is, okay, this f of xu is nothing but f of x bar, because that is what I know. Okay. But the fact is these guys will not cancel out anymore. Okay. If it is x hat, then x hat minus x hat was there, but now it will not cancel out, it will remain actually. So, a of t is evaluated at x bar now, del f by del x evaluated x bar, and C of t is del h by del x evaluated x bar. Okay. Again I am telling, if you take expected value of all these expressions, then expected value of f of x, this term will not go basically. This will become x hat minus x hat bar, which we will see recently. So, if I take now this expression is from Taylor series expansion and keeping first order terms only. Okay. Now, if you put expected operator here, then this is first term is as it is, but second term this term will not go, this will remain actually. Okay. Because this is no more x bar, so this is no more x hat. Earlier it was x hat, so x hat minus x hat was 0. Now it will stay. So, keep that, okay, keep that at times x hat minus x bar and all that. So, they propose this equation now. So, we tell okay x hat dot is this quantity, okay, what you see here and what you see here plus Kalman game times the actual measurements minus predicted measurement. Predicted measurement is this quantity, okay. So, minus this of everything actually, okay. So, put that way. So, y hat is obviously if you go back to this expression, this is by definition y hat is nothing but this one plus c times this quantity actually what you see here. So, the covariance matrix can be derived and you can derive it fully now. You can go back and derive this. So, something like P dot will turn out to be the full expression again, where A and C have to be evaluated around x bar, not x hat. Alright. So, that is linearized LKF, linearized Kalman filter basically. Okay. But in principle, it does not give too much of a benefit. It I mean honestly it gives us algebra complexity and things like that. So, people have thought okay why to bother so much about it actually. So, the most popular form is still there is Kalman filter, but sometimes LKF is probably beneficial to use it initially, okay, to get some form of some sort of conditioning of these numbers before you excite EKF and all that. So, the transient performance can be relatively better. Okay, so, that is the utility of this linearized Kalman filter in general. Alright. So, as I told before, Kalman filter has several concerns and all that. So, let us see some of these comments and the other things. So, first of all, LKF is less accurate than EKF since x bar is usually not close to x of t. Okay. So, what happens if you do this LKF in that form? Your nominal trajectory is always there. So, even though you have a better estimate, you are unable to use it actually subsequently. That is the whole idea there. But again LKF can lead to this priori computation of KET, which can be stored and used in online computation, which is not possible in EKF. So, sometimes as I told to avoid large initial stuttering of EKF, one can start with LKF and then switch over to EKF. Okay. However, okay, it is often possible, okay, this however it is it's often possible to start the EKF ahead of time. So, that means when you want to kind of close in or modify the your control guidance whatever based on the estimated information. Okay. So, you can actually start the EKF little more time in advance basically. So, then these transients are expected to die down by the time you are interested to operate based on this estimation information. Okay. For example, if you think about missile guidance application and all that, in the terminal phase you largely are interested in seeker based information because that is much more accurate, but that filtering can be actually initialized based on radar data. So, a little before, little time before, so that your better values of gains and other things are available by the time the seeker starts operating, or you close your guidance based on the seeker data basically. So, that kind of application, I mean usually it is done that way invariably, because the initial transients can be very bad. So, you start it little bit ahead of time and then tell okay by the time I want to use filtered information, transients are right down actually. Okay. So, essentially if you do that, then this necessity of first starting with LKF and then switching over to EKF and all that is also normally does not arise actually. and the philosophy of local iteration, that is LKF, can also be implemented here. Okay, and that leads to this iterated LKF concept sort of thing actually. Okay. But very rarely again we will hear terms like LKF in literature and all that. It is not very popular anymore because of no specific advantage over EKF actually. That's the bottom line here. So, there are various recommendations and issues for successful implementation of EKF. Let us study one by one. First of all, how do you tune it actually? Okay, that is a major issue, and the very first thing that comes to mind is something like this: fix R based on sensor characteristics. So, based on whatever sensors are available, we fix a number for R. Okay, then select P naught to be sufficiently high. In other words, we throw every information about initial value, and you tell whatever initial value of the state that you are guessing, this is large error actually. Okay. So, we take P naught to be very high, sufficiently high, and that has some ramification, that if you take P naught high, then it is going to converge much faster and all that actually. That's a tangent can be high, but it can converge much faster. Yeah. So, after these two, after you fix R based on the sensor characteristics and then select a P to be high, then what remains? It remains is Q. Okay. So, then you have to vary this Q up and down, in other words tune Q obtains until obtaining sufficiently satisfactory results actually. So, that is a kind of a universal recommendation for implementation of EKF. And again going back to that same thing, the filter should run sufficiently ahead of time prior to its usage, so that the error stabilizes before its actual usage. Okay. Otherwise, the initial error can be very large, and the associated control, guidance, everything can go bad, it can destabilize the closed loop system. So, this is a small kind of comment, but it is very critical for practical application actually. Okay. Also keep the measurement equation linear wherever possible, because see there are two choices typically: either we work with linear system dynamics nonlinear measurement equation, or you work with the linear measurement equation and nonlinear system dynamics. And typically if you have this formulas, I mean again going back to aerospace applications, you have this probably kind of a missile guidance problem, where in X and H you are looking at your dynamics and all that. Suppose the missile is here and some target is here, and the information typically comes in the form of something like r theta. Okay, this angle. The sensors will look in the framework r theta, but your inertial coordinates in the form of Cartesian coordinates. Okay. And hence if you formulate this dynamics in terms of x direction, y h direction, and also dynamics of target in terms of x and h direction, things like that, and it turns out to be something like a kind of a Cartesian problem actually. Okay. So, in other words, system dynamics can be in the form of Cartesian coordinates, where the measurements can come from the polar coordinates actually. So, now we have two choices. If you stick to that, okay, what happens is the polar coordinate information has to be converted back into the state space equation. That means, the r has to be expressed in the form of something like delta x whole square plus delta h whole square, like that actually, square root, and theta also, I mean tan theta is del h by del x and all that. So, in other words, the measurement equation becomes nonlinear actually. Okay. So, what about looking at in alternate sense? In other words, you tell, okay, my system dynamics is already in the form of polar coordinate. So, instead of this Cartesian coordinate dynamics, I will talk about polar coordinate dynamics. Then what? Because my measurement is already coming in the polar coordinates, okay, and that will make my measurement equation linear actually. Okay. And there are many observations from practicing people and some literature and things like that, that people have observed. Many times it may not give any specific advantage looking at this way or that way, but sometimes it can have some advantage when we formulate the problem where the output equations are typically linear, where the state equation can go nonlinear. So, either way you have to truncate anyway. So, somewhere you have to evaluate C and somewhere you have to evaluate A. So, the moment you evaluate that using Taylor series, there is some sort of truncation actually. Now, the question is where you want to do that, and the recommendation from some practicing people and things like that is that typically you prefer that the output equation remains linear actually, because there is no theoretical justification for that. Let me be very clear on that actually. Alright. So, this is what it is. What the next one? Okay, care should be taken, or sufficient care should be taken rather, to avoid numerical ill conditioning, and that can happen due to several reasons, including truncation errors and all that. Especially in early computers, the truncation errors were punishing because this digit, this floating point computation and all were very limited actually. So, you are truncating all the numbers very quickly, and then that was a major issue. Now that the 64 bits and all that, if you really want to implement, may not be a major issue, but still there are issues because of numerical problems. For example, many of these things can be written in several books, including this book, which I will again list out at the end of this lecture. But there are several improvements of algorithms have also happened over the period of time, which will try to avoid this kind of issues actually. Okay. And more of that you can read. So, for example, this P dot equation or this update equation that we discussed in discrete time domain, we want to use the symmetric expression of propagation rather than the asymmetric expression basically, even though that is a simplified formula. So, things like that, be aware of that actually. And here again the care should be taken to eliminate outliers, and outliers is something like kind of innovation actually. So, you have this innovation coming into picture in our implementation thing. Okay. So, this sorry here somewhere. Okay. This term, actual output minus predicted output. So, this term contains innovation actually. If it is very high for whatever reason at a particular instant of time or couple of discrete time interval and things like that, to tell there is something wrong might have happened because in the sensor or somewhere. So, that it is not giving me proper value. So, let me not correct everything based on everything blindly based on whatever I see. If I do that, my things can go very bad actually. So, let us not do that. So, it is possible, I will do that based only if the error is not very high. Okay. The error is reasonably okay, then I will update thinking that my measurements are good. The error is very high at some point of time, then it will okay, something bad has really happened, I do not want to kind of account for those things. So, I will ignore that rather and continue on the prediction mode basically. Okay, so that is another thing. But also remember some data rejection methods are also available, a little bit formal methods and all that actually, you can see that. And bottom line is EKF is little bit fragile, and in other words only a narrow band of design variables P naught, R and Q will exist. So, do not lose hope and have sufficient patience in tuning these variables, okay, for any given application. There are some recommendations that we discussed here, okay, this way you can start like that and then change values and all that. So, that is the tuning process actually. Okay, that needs to be done a little bit carefully with some sense of you should have sufficient patience to do that actually. It ultimately is going to work, and when it works wonderfully actually. So, have some patience to tune up actually. Then there are a lot of consistency issues in kernel filter, and there are a lot of checks and bounds available in kernel filter. So, there is something like sigma bound test, something like normalized error square test, something like normalized mean error test, something like autocorrelation test, something like Raman-Round inequality and things like that. So, there are various tests, and always subject your results with respect to some of these tests, and invariably it should have sigma bound test. In other words, your P matrix gives us lot of information, and the diagonal elements of the P matrix are essentially sigma squares basically. So, if you collect sigma and plot this plus or minus sigma or plus or minus 2 sigma and things like that, ultimately starting from any initial condition the error should come within that actually. Okay. So, that is called sigma bound test, and ultimately in any experiment this result should be kind of a must actually. Okay. Otherwise, there is no confidence on what you are getting. You may get a stabilized value or which may look good, but your P matrix may tell something and your estimation may somewhere else actually. So, that if that fails, then there is no sufficient confidence on the results basically. Similarly, other things can also be sensed. Whiteness test also, the autocorrelation whiteness test, all that. So, that means it turns out that your innovation quantity, if you test it out, you have from a very random variable or from a white noise, you have taken out kind of a continuous signal. So, it does not matter, the innovation will again turn out to be white actually. So, we can think about doing this test also and things like that actually. Okay. So, some of the difficulties in practice, computer round of errors are always concerns, no matter how whatever digit of accuracy we want to operate for a long period of time, then this round of errors can still have a major concern. Especially for onboard computers, they are still not based on very powerful computing and all that, where round of errors can be very punishing. Okay, so be aware of that. And something like if you have some error propagation happening and you don't check it, that unchecked error propagation can cause disasters actually. Okay. And asymmetry of covariance matrix is a large symptom of numerical degradation. Can you watch out for P minus P transpose norm? If you evaluate, that will give 0 if it is symmetric. If it is asymmetric, it will give you start popping up some numbers and all that, which can be thought of as some sort of a indication that things are going bad actually. Solution of Riccati equation, there are ways of doing that, and there is something called square root filtering, and this talks about some solution via holistic factorization and all that. I mean these are all the issues of implementation really. So, it is not like blindly I will implement something, get some answers actually. Yeah. So, this using this factorization, if you solve Riccati equation and then use that, then turns out to be much better actually. And in case of there are some large initial errors and you have absolutely no clue of how to guess it and things like that, there are ideas like information filtering available, and more I mean the filtering is itself can be a course and all that. So, there are many ideas there. I suggest that you read some of that actually. So, some points to remember, nonlinear estimation problems are considerably more difficult than linear problems in general. Again, EKF is just an idea and not cure for everything. Okay. The problem with nonlinear system is that Gaussian input does not necessarily produce Gaussian output. Okay, all these things I have talked it. Okay, so let us talk about limitation of EKF, and limitations turns out to be significant also. First limitation is linearization can introduce significant errors. Okay, because that problem is highly nonlinear, linearization is not a cure typically. There is no general convergence guarantee, and convergence observations are there, many times you may get it, but in general there is no convergence guarantee at all. Yeah. So, works in general, but in some cases its performance can be surprisingly bad. Yeah. So, typically it happens to be very unreliable for colored noise, and so some ideas like shaping filter is available, where you take a little bit subsystem and then put it to white noise as input, so that output can be kind of the noise that you are looking for, not necessarily white. So, that little that little block I mean this system dynamics can introduce additional states and things like that. This is called shaping filter actually. We have discussed that before, and we will take an example also next class onwards. In next class, we will typically take an example in one of the lectures later to see what is the shaping filter, how to implement all that actually. So, there are necessity for beyond EKF, and the need essentially turns out to be because of system dynamics is typically non-linear. Noise does not necessarily satisfy Gaussian PDF. Okay, so, non-Gaussian noise actually, and also we have this see noise is also a physical phenomena, it cannot happen extremely randomly basically. Noise happens because of certain characteristics. So, assuming that it is completely uncorrelated, that means whatever happens now is completely ignorant of what happened immediately before now, it is very unrealistic also. So, correlated noise or color noise is also always a concern. Okay, white noise, I mean we assumed white noise, it has given lot of zeros in the derivation and made the derivation lot simpler, but that does not mean that it is close to reality actually. So, we have this correlated color noise, then what actually? So, these issues will start popping up actually. Yeah. So, characteristics of this advanced filter are something like this. They are often approximate, not very good in some sense. They sacrifice theoretical accuracy in favor of practical constraints. So, what we are talking here? We are talking here something like advanced filtering, which is something called H infinity filtering, something called particle filtering, things like that actually. Those are available. Okay. There are Bayesian based filterings also, Bayesian belief based, and particle filtering happens to be one of the cases actually that way. So, these essentially sacrifice theoretical accuracy in favor of practical constraints, and considerations like robustness, adaptation, numerical feasibility like that actually will become issues there. So, essentially the attempt to cover the limitations of EKF and run into some other issue, if you can solve it, then turns out to be good actually. Alright, so we going too much beyond is not possible, but little bit beyond what is called as uncentered Kalman filter, we can have a glimpse of that, not a very detailed sense actually. So what happens here is motivation is something like that. There are tuning difficulties of EKF, we know that. So can it be relaxed, and in other words, can it be little lesser difficulty that way. Then the second motivation is this change of the characteristics of the noise PDF through nonlinear transformation. Okay, you can still characterize as some sort of a time varying Gaussian PDF, it is not stationary. Okay, it still can interpret that as a Gaussian PDF, but it is not necessarily stationary. In other words, this mean and variance will keep on varying actually. Okay, so if you consider it that way, then is there any idea that you can update this mean and mean and covariance of this PDF itself actually? So one line of thought which essentially started from Oxford University UK is something like this. Their idea is like, okay, Gaussian distribution properties can rather be propagated easily than the covariance matrix itself actually. So we propagate some of these distribution properties, something like sigma mu and all, then evaluate this covariance there once you do that. So there is no need of propagating this covariance matrix and running into difficulties actually. And it also gives us a platform, if necessary, we can approximate the higher order moments of the distribution after transformation as well. If you take more and more points, what are called as sigma points and all that, if you consider more and more sigma points, it is possible to compute higher order moments also. The moment it is higher order moments are also assured to be guaranteed to be same and things like that, your accuracy becomes more and more better basically. So this is a typical picture that appears in many of the literature and things like that. This is a very conceptually very intuitive picture. Turns out, let us start with a distribution with a mean and some sort of a covariance bound around that. And if you really propagate through a nonlinear function, it takes a different shape actually. So mean can go transfer somewhere else, and then the covariance can take a different shape altogether actually. Now the whole idea is how best we can approximate this. Now it turns out that if you transform this through this propagation ideas, then Py can take a very different shape actually. Okay. So essentially the true mean and variance can be somewhere else. Okay, this is your true mean and true variance, whereas the predicted thing turns out to be this is the mean and that's the variance. So obviously the properties of the Gaussian distribution gets distorted actually. What you should have actually got is something like this. Now the question is, okay, how about random sampling? You can do thousands and thousands of sampling and then pass everything through this nonlinear function and then re-evaluate the mean and covariance again, and then it will turn out to be close to that. That's how we can get an idea of what is going on here actually. Now the question is, this thousands and thousand points is not a feasible answer. It is not possible at all to do that. So it turns out, okay, can you do that in a minimum number of samples basically? So that is the whole thing that turns out to be some sigma point concepts and all that. So if I can selectively select, kind of judiciously select these points, and it turns out to be some eigenvector properties and all that will come into picture here. Okay, if I judiciously select these points, these are called sigma points, and if I pass these sigma points and evaluate quickly this mean and covariance, then it turns out to be very close to what it should be actually. Okay, that's the whole beautiful thing here. There is a minimum number of points using which I will pass all this through the same nonlinear function, and after I pass it, they will fall somewhere, and then I can quickly evaluate this mean and covariance. And again I will select a bunch of another sigma points based on this new distribution and then proceed further actually like that. So there is a simple example to demonstrate these ideas in this Dan Simon book. It's a very good book again. It's a polar coordinate to Cartesian coordinate. You have earth cos theta or sin theta. If you do that, if you do this linearized covariance, it turns out to be somewhere like this. If you do this sigma point propagation and find out again, then it turns out to be very close to what it should be. And that is all the whole idea which lead to this uncentered Kalman filter sort of thing. More details you can see it in this book also. Okay. So we have this very quickly, we have this linear dynamics all in discrete domain, measurement equations also like that. The entire equation concepts are taken from this book. More on that, there is a good chapter around that, you can read it actually. So this is what it is, and then there are some other thing that I saw from a different literature. I thought of putting it here. what do you mean by sigma points actually? So, sigma points is a set of weighted sampling points and things like that. So, you can one on the tip and then 4 outside and things like that you can see actually. Okay. So, these sigma points are propagated through the true nonlinear function using this functional evaluation alone, and there is no analytical derivative used in order to generate this posterior sigma points. These are selection, we pass it through the nonlinear function and there is no derivation, derivative information involved. Jacobian matrix is completely avoided actually. Okay. Then the posterior statistics are calculated or rather approximately calculated using this information actually. These definitions are taken from this reference really actually. Alright, so how do you implement it without derivation again? You initialize this the initial condition and noise, the covariance matrix. Then select a bunch of sigma points, something like this. Okay, 1 to 2n, sometimes 2n plus 1 people recommend, sometimes 2n. This center point is type of kind, sometimes you are not there basically. So, you use the selection of sigma points, you select a bunch of sigma points like this 1 to 2n. Okay, and n is the number of states, remember that. So, first 2n, first n are evaluated square root of this and then the rest evaluated of this actually. Okay, k plus 1 the negative of those. So, these are symmetrically placed basically. Remember as long as there is a positive definite matrix, we can talk about a square root of that also basically. So, we can do that, then transform the sigma points and then calculate the new mean and covariance. This is as good as that. And once you have that, okay, you select the sigma points again based on the updated value and then proceed further. That is the whole idea there basically. So, transformation of sigma points can be done using the same nonlinear equation that we know. So, there should not be too much of a difficulty, and you can based on this you can have this predicted measurement as well actually. So, how to implement it? After you do this transformation there, you evaluate this py, pxy and then evaluate this Kalman gain and then update and things like that, update the state and update the covariance again. So, this very quickly what it should be done, very easy to implement also in my view, and computationally it is not very taxing either basically. So, there are other concepts which I am not talking here in this course. There are concepts like particle filter and all that. We will deviate too much other side instead of retaining these optimality concepts and all that actually. So, these are based on Bayesian belief and things like that. But there are also nice concepts out there. If you are interested, you can see some of these particle filtering ideas again. There is a nice diagram in this book also. I thought I will put it here. There is something like computational effort versus increasing accuracy. So, UKF, well, even though the diagram is like that, I do not think it is too much computationally taxing. It may be little bit more than EKF, but not too much. Remember, EKF you have to evaluate Jacobian matrix, whereas UKF we do not actually. But UKF you have to use square root of that matrix, is also kind of computationally taxing actually. Okay, so that is what the difficulty. So, a little bit computationally more involved, but increasing accuracy. But if you have that advantage is there only when there is a nonlinear system or non-Gaussian noise and all that. There is a linear Gaussian system, you are unnecessarily wasting things, you are not getting performance improvement at all actually. So, be careful about what you are doing. So, that is all I want to talk in filtering ideas and all that, but I have listed out a few books and references for your convenience again. And those of you who are more interested can see these books, or classic books actually. There is a second edition available in 2012 also about this book. Many of my derivations have been taken from this book, but also this Dan Simon book is also very good. And other things are also there, especially this one is very practical related to missile guidance and things like that. And there is a first book that appeared, it is very popular among many several teachers and authors and things like that. And you can also see this, they are written by practicing people with very good practical implications, how to implement numerical schemes and things like that. And I also put some of the publications which appeared, this is the first original famous paper from Kalman. And it was appeared in ASME journal Basic Engineering. Then these two papers are really nice stories out there, fascinating perspectives of state and parameter estimation technique, and then a relook at the concept and complete competence of Kalman filter and things like that. Those of you are more interested to read fun stories and all that with some degree of insight that you want to gain, then you can read some of these. That is all I want to talk about Kalman filtering actually. Thank you.